So, hello and welcome everyone to this seminar. Thank you for coming. This is the last seminar given as postdoc Vatsal here in the team. So the floor is yours, Vatsal.
Thank you. Well, thanks for the introduction. Well, thanks for all of you to be here. It's good to see that we are back to our normal, normal, let's say, attendance. Well, today I will talk about so long and thanks for the flow. So as David said, this is going to be one of like the last seminar as postdoc that I will give here. And so in 7 years, we had a lot of fun and I did a lot of things and I can summarize them in basically what we did. What we did here together was complex multiphase flows. And as Detlef always says that we must do things and think about the relevance as well. And that's, I think it's crucial. So I will just walk you through from the things that I've learned and the perspective and the relevance that we have for complex multiphase flows. The first one is, let's say, if you think about industries, where you have some interfacial flows, which are complex. By complex, I would mean two things. So either rheologically complex or complex because of geometry. For example, here you in injection printing, we have these jets that come out, and then if you have water, it breaks into satellite droplets. If you add polymers, you can suppress it just enough. Whereas if you add too much polymers, by too much I mean, I think Udo can correct me if I'm wrong, but probably 0.01%.
Now
then it stops.
Add another 0.
Yeah, okay, another 0, and then it stops jetting. Of course, it's also relevant for pesticides because there also you can add polymers, and then you can make your pesticides stick to the leaves when you throw them on plants and stuff. This is also important for 3D printing, and let's say since we're in Netherlands, also in mayonnaise and toothpaste. It also is important for healthcare, and I think Ayush gave this PoF seminar last week, and he spoke a lot about let's say the processes that go on over here with the breakup of saliva and so on. What is also which also formed like a basis of my PhD was these two videos. In fact, so this is blood. I learned later on that this is not human blood but pig blood. Experiments done here at PoF, but way before I joined. And this is impacting droplets on paper and on fiber, on clothes. Also, if you think about energy transitions, there also you have multi-phase flows, which are complex, but not because of rheology, but because of geometries that we use. In principle, if I were to summarize my time here, I did some work on droplet impacts, also on bubbles. In fact, if you look at the PoF website, then the byline reads, the DNS of drops, bubbles, and jets. So this is a drop, that's a bubble. There's also a bubble inside over here, and there are 3 jets that you see in this slide. Also, towards the end of this time, I also did some work on sheets, and now this brings me to the big dilemma that I faced coming into this seminar for the last, let's say, 1.5 months or so, is what to speak on, because each of them could be quite a bit of, let's say, long seminars, which I of course would not do to you. So I decided to then spend the time on droplet impact, because this is one common theme which was there 7 years ago and kind of continued also throughout. So I will speak today on impacting droplets. And of course, this journey on droplet impact particularly has been long, and there have been several people who have contributed to this. The blues are the experimentalists, the yellow ones are the numericists, and the orange ones are the theoreticians, and also the people who would start are currently in the audience. So Udo is here, Detlef is here, Jaco and Aman and so on. You're all here. And what I won't talk about at all today is the underlying framework that has helped us to achieve all these results that I will show you in a minute. And that has all been done using Basilisk and also things that we develop on top of Basilisk. But I won't go into details of that. Well, of course, everything that we do is open source, and you can always just come to us and we can answer. What I do have on the menu today is some starters and then some main course and some dessert. So I will start right away with what are impacting drops. And I would, with raise of hand, can anyone tell me if you have not seen this video from me before? Oh, okay, that's what I thought. So this is basically a water droplet where someone is playing a ping pong with 2 superatomic paddles, and the droplet is going back and forth between these 2 paddles. And of course, you would like to do this in a more controlled way, so not in space but on Earth. Then you can do this in lab by throwing water droplets on surfaces. So here, if you throw them at small velocities, or you throw them at high velocities, then they can either shatter or they can also show some very rich phenomena over there. When you look at these videos, we can ask many questions. For example, what is the maximum spread of these impacting drops? So when you throw them on surfaces, how far do they go? What is the force that is exchanged between the drop and the surface? And of course, as you saw in the video where Scott was playing ping pong with water droplets, when will this drop stop bouncing, or will it continue to bounce forever? So those are several questions that one can ask. And if we boil this down in physics terminology, because as physicists, we all love dimensionless numbers. So the numbers that you will keep hearing over and over again from me is this Ohnesorge number and the Weber number. The Ohnesorge number is a sort of dimensionless viscosity of the droplet, which is a proxy for dissipation in the system, if you may. And Weber number is like a dimensionless kinetic energy of the droplet, which will control how fast and how deformable these droplets are. And once again, we will ask the question that how much will it spread, how much force it will apply, and when will it stop bouncing if it bounces back and forth, as we saw. And just to give you an overview of the process, so these kind of videos you will see quite often during the talk. On the left-hand side, I would always plot in these colors log 10 of viscous dissipation function. Black means high dissipation, white means almost no dissipation. Whereas on this side, I would plot the normalized velocities, where dark blue means close to impact velocity and white means almost, let's say, zero velocity. And any drop impact process can be split into 4 parts. So one is the impact. It falls, it spreads, stops because of surface tension, comes back because surface tension wants to minimize surface energy. It cannot go down because there is a surface, right? So it has to go up, so it will recoil, and then ultimately it takes off in different shapes. So in this case, it looks like a bowling pin, if you may, right? So it can take several shapes as it goes away. So with that, I would start now with let's say the force of impact. So how much force does this droplet apply on the surface as it falls down? And in this, the way we do this is in experiments is we simply put a force sensor under the superhydrophobic surface and measure how much force the drop applies on the surface. And in numerics, it's even easier. You simply integrate your pressure and you will know how much force this drop is applying on the surface. And with that, with these ingredients in, now we get this video. So here you have experiments, over there you have simulations, and in this plot there will be an experimental line and a simulation line. And I would just let it play and take the glory of this insight, because there are no free parameters here. So we simply do the experiments, get the control parameters, Weber and Ohnesorge number, run the simulations, and out comes these results. Yeah, Tommy. Oh.
No one is trying to enter.
Maybe David, you can send like just this link once again to PoF Sam. So we'll fix it. So well, okay. So coming back to this, so we have so in red there's simulations, in blue there's experiments, and there are 2 peaks here. This is something that also I will speak about a few times. So the first peak is kind of obvious, that when the drop hits the surface, it comes to rest in the vertical direction. So we must have a first peak. And the second peak as well, it's also kind of, let's say, intuitive in the sense that when the drop goes away, then there is another peak in force. Why do we have 2 peaks at 2 different locations? That's because of the different phases of drop impact. So the spreading, the impact phase over here is isolated from the spreading phase. So there is a separation of time scale during impact. So it impacts, spreads out, stays on the surface, let's say momentarily, and then comes back and takes off. And this is something that you should remember, because I will come back to this later on. And if you think about this just with these 2 control parameters, with the Ohnesorge number and Weber number, in fact, we can cover quite a lot of ground in terms of applications like rain droplets or respiratory droplets. Of course, Alvaro, Tommy, and Detlefeld, you would, well, also you will complain that respiratory droplets are not Newtonian. So, but this is, if you imagine them to be effectively a Newtonian liquid, then you would project them over here. But of course, they lie in a separate dimensional space. So that's the 3rd dimension, which I don't show over here. And then if we, so what I really would like you to remember or take home from this talk is that if you want to understand the entire parameter space, you must really investigate each and every corner of this. And this is our attempt to do it. So each data point here shows a set of 4, if I'm not wrong, simulations, which is now condensed into 1 point over here. So we cover the entire parameter space. and ask the question, what is the maximum force applied by the droplet and how much it spreads when it falls on the plate.
So what do you need to do for simulations? Was have a stochastic element? Or?
No, this is like it's each data point represents force simulation in the neighborhood.
Okay.
So it's just to at least that you can at least see that there are data points there. Otherwise, you won't see the data points. So in total, I think there are 16,000 or so.
There's 5-dimensional.
Yeah.
To save dots. So to say.
Yes. Okay.
And then we ask the question how much force the droplet applies and how much it spreads. And just to give you an overview of why these four, let's say, parameter spaces are distinct. So if you live in the small Weber, small Ohnesorge regime, then you basically end up with a droplet that deforms quite a lot. It throws capillary oscillations, and we get shapes like this, where almost the deformation is there, but it's not that high. Whereas if you keep the Ohnesorge number small but extend the Weber number, so then you get something which are pretty extended out, where you have initial shape is still at the instant of maximum force is still not that deformed, but then it deforms quite a lot, as you can see over there. It has substantially gained surface energy as it expands. Whereas if keeping this Weber number fixed, if you increase the Ohnesorge number, you once again you go back to something that looks like a pancake, but then it's quite different than this shape, because now also if you see here, the velocities inside the drop is completely gone at this stage, and also it's completely like a thick blob, as if you may, over there. Whereas if you then go to the fourth, let's say, extreme of the parameter space, where it's highly viscous and coming down at a small velocity, then essentially it deforms a little bit at the south pole. It comes down a bit, but then it just pretty much stays there because it has lost all its energy. And so when we look at the different phases of this drop impact, if you may, what we could then okay, before that, so of course we are not the first ones to look into this question of how much it extends and how much force it applies. And the current state of the art before we came into this is this very nice work where authors tried to empirically bridge between the inertial limit and the viscous limit. So instead of thinking of this as four distinct parameter spaces, if you thought of this as, okay, it can either be inertial or it could be viscous, and then you can do some scalings. And then if you do an empirical fit, then you get this grade over there. And the data points in, let's say, for water, so Ohnesorge number of 0.0025 is that of water, agrees relatively well, except that the shape is wrong. But other than that, it's the correct order of magnitude in terms of, let's say, the numbers. Whereas now if you go to higher Ohnesorge numbers, so now if I go to something which is, let's say, 100 Ohnesorge number is pretty viscous as compared to water. That's roughly, if I'm not wrong, let's say 4 orders of magnitude more viscous than water. So think about a very highly viscous silicon oil, if you may. And then the data points are further off. It's quite away from this line here. So the question is, can we do better? So can we formulate like a expression where we can cover all these different extremes? In the interest of time, I won't go into all the, let's say, calculations, but it's actually pretty straightforward. What you have to realize is that well, there is an energy conservation involved in this process. So at the beginning, you have all the energy is stored in the kinetic energy of the droplet. It falls and it spreads, so it gains surface energy, and it also loses energy because of viscous dissipation. And if you account for all these energy scales, then you end up with, let's say, if you do the energy rate balance, then you get the force, which depends on the control parameters. You can realize this is the Weber number, and this is just the inertial force scale. And it depends on the rate of viscous dissipation that I write down over there. I will come to that in a minute. And on the second hand, if you do an energy balance, then you get the maximum spreading diameter, which also has a dependence on in the leading order on the Weber number. And then there's a correction because of the viscous dissipation. So one thing that you would immediately realize is that viscous dissipation is the key, because that's the only thing which I have not filled in. Okay. Other things you can get very good estimates or very good rough idea about the scales involved for the other forces. Just again, the take-home message would be: if you do an energy rate balance, you get the force. If you do an energy balance, you get the diameter. The details you can discuss with me later on. And the second key insight for this in this process is again the separation of time scale in this let's say problem. If you look at, let's say, the spreading diameter d as a function of time and the force as a function of time, you can identify two distinct, let's say, temporal sequences. One is when the force goes from 0 to F max, And in this time scale, the droplet barely deforms. So you can see that the south pole has deformed a bit. It exerts like a inertial shock, because when the drop is falling down, it hits the surface and it just the south pole stops immediately, and then you can look at the scales which are involved in that process. But that happens on a very fast time scale where the droplet deformation is minimal, if you may, here. Whereas the second time scale, which is long, where the force from force maximum goes to 0, which is as a stage of maximum spreading, there the deformation is large. So there are two distinct temporal time scales, one where the force increases from 0 to F max, and the second where the deformation goes from minimal to spreading out quite a lot. And if you do this, let's say split of time scales, and we fill in the exact, let's say, scaling laws for the different, let's say, dissipation mechanisms, then you would end up with basically, for the forces, you can still get away with having two distinct regimes. One is the viscous regime, where the moment the drop hits the surface, if it has high enough Ohnesorge number, the dissipation would be immediately in the entire droplet, and that gives you certain scaling. Whereas in the inertial limit, when the drop hits the surface, the boundary layer where the dissipation occurs is nested inside the bigger droplet, which we can also calculate. And then these two scalings would help you cover this parameter space of Ohnesorge across quite a few orders of magnitude that you see on here. Of course, a 3D plot is not a good representation for such a system. So what we do is we take slices over here, and then we show in the slice of, let's say, Weber number at different Ohnesorge numbers and Ohnesorge number at different Weber numbers. And the expressions, again, by filling in the rate of viscous dissipation in the previous, let's say, equation that I showed you, you can get these black lines that you see over here, where you can predict what's the force of impact as the drop hits the surface. Similarly, another, let's say, take-home message is that there are no pure scaling laws. So if you were to do scalings over here, you would get certain effective scaling laws, but you won't get any pure scaling laws from here. On the second hand, that becomes a bit more tedious, but by tedious, I really mean tedious in terms of calculation, but really elegant or simple in terms of, let's say, formulation, because it's nothing. It's simply you have to calculate to find out the different dissipation scales and simply fill them in. Of course, now you have to think about what happens during the impacting phase and the spreading phase, and they can have different features between them. And if you do that, you end up with this again, with this 3D space, which once again we show in terms of, let's say, slices. So here, once again, the black lines are from the theory, and the data points are from the direct numerical simulations. One thing to note here, which I will again come back to later on, is this upper bound here, which if you were to ignore viscous dissipation, and you would say, okay, let's simply assume that all the energy that is in the kinetic energy of the drop goes in the spreading phase, then you would get this gray line over here, which works fine as long as you're in the low Weber number regime and low Ohnesorge number regime. But as you go to high Weber number, then obviously viscous dissipation matters. But also when you go to high Weber numbers, then also the dissipation matters, and then it actually deviates away from this inviscid prediction, if you may. Once again, there are no pure scaling laws over here. So yeah.
So you did not show what are you showed this expression, and then there's this dissipation term that is tricky. So is that what, if you go back to your previous slides with is that the different regimes where you have different estimates of dissipation?
So here, when you look at basically, so you have to realize where the dissipation occurs. Is it nested inside the drop? Yeah. Is it nested? Is it bounded by the radial extent? Is it bounded by the height, or is it all over the place? And by simply, so it's not so much about the scales of, so you have scales of velocity gradients that we must find out, but also scales where the dissipation occurs. And we have good estimate of this also from numerics, so we can see from numerics where the dissipation are, and we can isolate that, and then we can make good predictions of where that would be. So one paper which also was quite helpful for us in doing so is this 2010 paper by Jens and Stefan Zaleski and Christoph Jossera and so on, where they have pretty good idea about the different scales which are involved, or different, let's say, reasons which are involved, and you just simply have to extend that to other regimes.
So when you say you compare to the theory, it means that the theory uses different ingredients depending on where
you are in this parameter space. Yes, and then DNS we simply do the DNS. Yeah. Well, okay, so all well and good, but what comes next? So what is next? So we could answer this, let's say, Newtonian drop impact across several decades of Ohnesorge and Weber numbers. But of course, we want to do more. And so for more, then we had a pleasure to work with a very nice colleague of ours who is also now here, Somili, who joined also our group as PhD, but this is not her PhD work. It's her work from internship here. Also, John Kolinski is now doing some experiments for us on this, and of course, Detlef. And what we are going to look at here is that there are two cases. One is a viscous droplet falling on a plate. So it's this one here. And the second case that you can think about is when you have elastic beads or soft solids falling on plates as well. And then this we can model as a viscous liquid. So basically, your stress and strain are linearly related with this equation. And then on the second hand, we have a solid impact where we model this as let's say a Kelvin Voigt solid, or you can think of it as a viscoelastic solid, where we have a viscous term, which is the dissipative part, which we try to keep small for now. And then there is a let's say elastic part, which is dependent on this elastic modulus G. And there is A minus I is the strain or in the system. And if you think, and these two problems are actually, they have a very rich history, because the first problem was kind of looked at by Wagner back in 1932. And this is the problem where where we have certain scalings that you see over there. And the second problem here for solid impacts, for the, let's say, soft solid impacts, was looked at by Hertz. This was in 19th century. So I think pretty much 40 years or so before the liquid impacts were a thing. And then in both these cases, what is kind of remarkable is that the footprint of these two droplets as they hit the plate have the same scaling, but with different prefactors. And the prefactors here come from the matching, in the Wagner case, come from matching of the solution as you at the footprint of this droplet with the ambient, which is air. And in this case, it's also there, but the prefactors are really different, that you can see over there. The second part is the force scaling, as you saw also in the previous slide. So the force would scale with the inertial pressure force, which is rho v naught square r naught square. So this is still inertial force over here. And you might comment that, okay, Wagner predicts this force, but if I look at my problem statement, and if I were to do Buckingham pi, you could still get this force scaling out of it if you simply balance the terms or balance the dimensions actually. On the second hand, when you look at solid impact, there is no way, I mean, you could still say, okay, there are two force scalings. One is this elastic moduli times r naught square, that gives you a force. And also the inertial pressure force is also still present. But this, let's say, the split between 2/5 and 3/5, so the different partitions of gr naught square and the inertial pressure force, of course, you won't be able to get that by purely by scaling. But of course, if you are smart as Hertz, you can actually calculate that as well. And if I just show you two, let's say, test cases. So in one side you have liquid impact. On the second hand, we have the solid impacts. When the liquid drop falls, it spreads. Whereas the solid droplets, as it falls, then it goes back. These two things happen on the, let's say, the same time scale, as you can see here. Dark blue again means 1, so the velocity of 1, the same as the impact velocity, and white means 0. And so if you look at the liquid impacts first, so this is a plot that I have shown you already, but this was now in a bigger parameter regime, but now only for, let's say, water or 2 times more viscous than water. Even if you go to something which is now 100 times or roughly 100 times more viscous than water, this force scaling that comes from Hertz in the limit of large Weber numbers is pretty robust. Everything collapses on this horizontal line over there. So in fact, for small enough Ohnesorge numbers, the forces are also remembered in the previous, let's say, part of the talk, where the forces were still, you were still able to get away with it by simply dividing them into inertial part and viscous part, unlike the spreading part where we had to take care of 4 different regimes. So the force scaling is more generous in the sense that even if you go to something which is 80 times more viscous than water, the maximum force doesn't really change that much. Of course, there is some small Weber number capillary corrections, which is over there, which I won't discuss now. But in the limit of large Weber numbers, it all goes to a constant value if you take the correct compensation over here. So what I do is I take one set of data points from there. I have also changed the length scale from diameter to radius. Sorry about that, but this happens when you have different projects and you try to combine them together. So now it's the same plot as before. In the large Weber number regime, which simply goes to a constant value, as you see over there. Now what we are going to do is we're going to play a game where we will basically keep the elastocapillary number. So this is the dimensionless elastic modulus, if you may. So the Weber number was a dimensionless kinetic energy, Ohnesorge number dimensionless viscosity, and elastocapillary number is a dimensionless elastic moduli. And if we keep the elastocapillary number constant at 3 values, so 0.1 to 10, and we vary the Weber number, we end up with these data points that you see over here. Of course, what we notice that if you throw them at high enough Weber numbers, they still converge back to the, let's say, the liquid-like scaling, which is over here. And if I show you the video, which is this one, you also see that it actually deforms quite a lot. So the idea is that if you have a soft solid and if you take it and you throw it at extremely high velocities, it is still going to deform and it's still going to give you the same force signature as if it was a viscous liquid droplet, as you see over there. The scaling pretty much collapses there. On the other hand, if we play the same game again and by increasing the elastocapillary number even higher, so 100 and 1000, then we start to see systematic deviation away from this viscous, let's say, prediction that we have with this gray dashed line over there. We can do it, and also if I show you this point here now, so this case, there are a few things that you would notice. One of them being that this droplet falls down and then also goes back up. Remember when liquid droplets would fall down, spread, and then take off, then we had 2 distinct peaks, right? Because there was a separation of time scale between impact and takeoff. Whereas in this case, there is no such separation. The droplet falls down, stops momentarily, and goes away. And this all happens within, let's say, a single time scale, such that you only get 1 peak in the force. And this is very similar to the, let's say, the force time diagrams that we would draw as in high school, where if you look at the forces which are encountered by billiard balls or elastic balls as they hit the wall and come back, these are symmetric forces around a central maximum, which you see over there. And that's because there is no spreading phase. The impact and takeoff occur at the same, let's say, time scale, and it's symmetric around this maximum. We can play the same game again by instead of varying the Weber number by keeping elastocapillary number constant, we can vary the elastocapillary number by keeping, let's say, distinct values of Weber numbers over there. And what you see once again is that in the limit of elastocapillary going to 0, we still recover the Wagner scaling. So that was these lines over here. Whereas now systematically, you start to see deviations away from this, and we start to see some feature of these let's say, power law that you see over there. So the question we ask is, can we explain this dependence on the Weber and the elastocapillary number? Or to reframe it, can we explain this behavior where in one end we see the Wagner scaling and in the other hand we see some Hertz type of scaling? And the answer is yes. We can do that if we realize that what matters is this elastic number or elasto-inertial number, if you may, where we normalize elastic modulus with the pressure scale, which is rho v naught square, and then essentially all the data points that I showed you throughout this talk in the previous all the slides, they all collapse into this one master curve, where in the limit of small elastic numbers, so elastic numbers going to 0, where the inertia is less dominant than the inertia is more dominant than the elastic stresses, it all converges to either the Wagner scaling or the Wagner scaling corrected with surface tension over here. Whereas in the limit of large elastic numbers, everything collapses on this one single line, which has a power law of 2/5. And if you were to plot the Hertz, let's say, force scale with this normalization, you would also get the 2/5 power law over here. And in fact, it's not just the scaling there, but also Hertz, unlike Wagner, because in Wagner, there is no prefactor. So the Wagner only gives you a force scale, but does not give you a prefactor period. But with Hertz, we know that there is a prefactor, which is roughly 5.13 from numeric. So this dashed line here is 5.25. And in my definition, that's a pretty good agreement between theory and, let's say, numerics. What we could also do, and this is a plot which I received this morning from Somily, is that you could also extend the same idea of the previous slides, where we were trying to compare against several orders of magnitude in viscous Newtonian liquids. If we were to extend that theory to also account for elastic stresses or elastic energy stored in the system, we can also get these lines that you see here, which then now also account for the elastic contributions. Okay, so with that, I covered, let's say, two parts, the impact force and the maximum spreading diameter. But of course, you saw these droplets are also taking off, right? So they're also going away. And for that, so most of the things that I've shown you now is more general solutions, in the sense that they cover across wide range of parameter space, and they are valid across several decades in Weber number, Lasker-Capri number, Ohnesorge number, and so on. But there are also certain parts of this parameter space which are quite peculiar. And what do we mean by peculiar? So I would show you one case, which is Weber number of 9. And this is again experiments, simulations, force with blue experiments, red simulations. And we see, well, first of all, we see the force rises, reaches a peak there. Then there are these oscillations. These are capillary waves that you can correlate on the top of this drop surface over there. Then it creates bubble cavity here, which collapses. And as this bubble cavity collapses, you get a very sharp increase in force. And so this sharp increase in force, in fact, is related. So this increase in force is related to the formation of this singular Worthington jet, because the curvature locally diverges at the axis of symmetry and leads to this very sharp increase in force over there. And this is something that we will understand. But the question is, okay, if it's a singularity in the curvature in this system, is there a way to kill this singularity? So how can we normalize it? And one of them is through viscous dissipation. So if I now show you 3 cases, the same video I showed you before with water at Weber number of 9, and then I subsequently increase the Ohnesorge number across this board, and you would then see that basically this one still forms this sharp singular jet, including this bubble over here. Whereas the first thing that happens is the bubble goes away, and then if you increase the Ohnesorge number even higher, then this jet also goes away. And this is again, this has a signature in the forces, because the force that this drop exerts in the second peak is much smaller than the first one. And in this case, the second peak is basically negligible as compared to the other two. Another thing that can happen is, instead of increasing the Ohnesorge number or increasing the viscous dissipation in the system, we could also change the impact parameters. So from Weber number of 9, we can go slightly lower. So this is again the same video I have shown you before at Weber number of 9. And we can go to 5, we can go to 12. And then what you would see here is that they almost look identical, except that the peak are blunted out. So the peak no longer exists. Or they are quite, the singularity in the peak no longer exists between Weber 5 and Weber 12. So what we have now is that in the parameter space of, let's say, Ohnesorge and Weber number, so in the color code, we have the force, normalized by the inertial force. We have a small island, pretty much, where the second peak is singular, in the sense that it simply diverges as the bubble cavity as the cavity collapses, and we get this very sharp increase in force. And this is also the reason where we have this bubble entrainment as well. And one natural question that you would ask me is, why is this at Weber number of 9, right? And why is it localized over there? I won't be able to answer this question to you, but if you remember from the seminar of Aman, who is also somewhere over here, he will try to answer this question, and probably next time he gives the seminar, he can answer you why this peak happens at Weber number of 9. But with the limited time that we have, we could explore this parameter space, and then it also landed us on the cover of JFM. And so this is the Worthington jet that you see over here, which occurs in this parameter space, well, the singular Worthington jet that occurs in this parameter space. And in fact, I have a hypothesis that JFM likes Worthington jets quite a lot. And the reason I say that is because within a span of like small time scale, there were 2 JFM covers, and both of them had Worthington jets on the cover. So I think Worthington jets are worthwhile to study, if not for anything else, for this reason. Well, okay, I'm pretty much towards the end of my main course now. So we talked about forces of impact, maximum spreading diameter, also the force that is exerted when the drop goes off. But of course, every time you see this video of Scott Kelly playing ping pong with water droplets, you can ask the question, when will this stop, right? So when will this drop stop bouncing? And if you remember this plot, so from the previous, I had this dashed line over here, and this dashed line is, we call it bouncing inhibition. So basically, if the drops don't bounce, they're not gonna exert the second peak, right? So there won't be any second peak if they don't bounce at all. So first way to do that is again through viscous inhibition. So this was a very nice, let's say, paper which came out pretty much in the middle of my PhD. So you go from water droplets to something which is 200 times more viscous than water. And what the authors claimed in this paper was that, okay, you can even droplets which are almost 200 times more viscous than water, you can even make them almost bounce. Where I would interpret this as the moment you extend the viscosity to large values, you can inhibit bouncing. So you can stop the droplets from bouncing. And why does this happen? So if the length scale of the droplet is much smaller than the viscous, the visco-inertial length scale, if you may, then the dissipation takes over in the entire, let's say, throughout the droplet. Again, going back to the previous plot that I had. And in that case, you get a critical Ohnesorge number, which is of the order 1. And at this critical Ohnesorge number, you can expect that whatever kinetic energy the droplet was bringing in, there will be a time after which all this energy will be gone, and the drop will not be able to bounce. And in fact, if you look at these two videos over here, before that, you can also do simulations, of course, where you can see this is the Ohnesorge number of roughly 1. So basically, when this value is exactly 1, and then this drop falls down, immediately dissipates all energy, and then slowly recovers back, because in this case, the bond number or the gravity was turned off, so the droplet will ultimately become spherical towards the end. And so at 1, we should expect a transition to non-bouncing. And in fact, if you look at this paper, the critical Ohnesorge number for stopping this droplet from bouncing was 0.8, so very close to 1, in fact. On the other hand, what about heavy droplets? So in this case, I only spoke about, let's say, bond 0. So bond 0, or you say turn off gravity, what does it mean? That our droplets don't have any weight, right? So these are same droplets as Scott when he was playing this, playing ping pong in space. Whereas, what about heavy drops? So what about Earth? I mean, you want to do experiments on Earth as well. And if you do that, then essentially the argument that you can make, the similar argument is that if my radius is much higher than the capillary, let's say, length scale, that the drop is way too heavy for it to retract, then the drop will stop bouncing. And this is what happens here when the bond number is roughly 4, so much larger, so larger than 1. And the drop, after it falls, it undergoes it undergoes surface oscillations. It will retract, come back, go back again, but it will never take off from the surface. So if you look at the parameter space of bond, so think of bond as dimensionless weight of the droplet, and the Ohnesorge number, dimensionless viscosity of the droplet. If you look at these two cases here, then essentially we have, let's say, the drop will stop bouncing if we exceed the critical Ohnesorge number. Whereas, and what we can also do is we can look at the restriction coefficient, which is the takeoff velocity as compared to the impact velocity of the droplet. And essentially, if you go to the limit of 0 Ohnesorge number, then the velocity, the restriction coefficient is constant, whereas it falls down and goes to 0 at finite Ohnesorge number, as you see over there. And you can again vary your Weber number and essentially explore all the places where this drop will stop bouncing. So it happens very close to this, let's say, critical Ohnesorge number of 1. In the interest of time, I won't tell you about these lines that you see over here, but you can come to me and we can also discuss where these lines come from. But there is a reason over here, which is close to Ohnesorge number of 1, where irrespective of how large a Weber number is, between 1 and 50 in this case, the drop will not bounce. It will stop bouncing over there. And in fact, the saturation of these restriction coefficient to a constant value, that also we can explain by realizing that even in the limit of, remember from the previous plot, where even in the limit of inviscid or like close to 0 Ohnesorge numbers, we could still, we were not able to make correct predictions if we ignored viscous dissipation. In the same way over here, if you look at the different energy, let's say, contributions, the viscous energy that is lost or the viscous dissipation that occurs during the impact process never quite goes to, let's say, 0. So that will be the difference between the yellow line and this line. I mean, forget about everything else. Just look at this this gap over here. And when the limit of 0 Ohnesorge number, this is quite substantial. And this is for Weber number of 1. If you go to large Weber numbers, and remember the maximum spreading diameters were off by quite a bit as you go to large Weber numbers. So once again, if you go to large enough Weber numbers, you get quite a lot of viscous dissipation, which is in fact more than 50%. So this is roughly 70% of energy is lost, even for really low Ohnesorge numbers. So water sits over there. So this is let's say 1/3 of viscosity of water, and even those cases can have a lot of, let's say, viscous dissipation, even in the limit of let's say 0 Ohnesorge number. And well, the bond number is less. Well, it's also nice, but it is less involved because, well, if you are heavy enough, then you won't be able to bounce. That's quite intuitive. And so if you think about the parameter space, since I am running out of time, I'm not going to go into too much detail of this, but essentially you can divide this parameter space into 2 parts, so bouncing and not bouncing. From all the things that I've shown you before, if you are beyond Ohnesorge 1 or beyond a bond 1, then you won't bounce. And this is also confirmed, or like slightly confirmed, by data points that you see over here, which are, let's say, from these experiments. But of course, what happens if you are inside? So there are these 3 cases, which all 3 of them lie somewhere over here. Okay, so here this one will bounce, as you will see, but these 2 will not, even if their Ohnesorge and bond numbers are less than 1. Why do I show this? Well, I showed this because I'm going to take, just bear with me, I'm going to take slight, let's say, I will go slightly forward, because this is also to tell you that not always, the answer is not always clear when you start a project, because the story that I'm telling you about came later on, as compared to this paper that we worked on together with Jaakko, Srinath, Pierre, and Detlef, where we were quite puzzled by the fact that there was always cases which were under these 2 asymptotes, because these 2 asymptotes were well, quite intuitive, as you would have seen now, right? But there are always data points below these asymptotes which won't bounce. So this is the star over here, and that essentially took us down this road where we looked into these 3 cases where, let's say, these 2 cases, even if they are below these 2 asymptotes, would also not bounce. And how do we explain this? In the interest of time, I won't be able to explain it to you, but what I will tell you is the answer lies between taking an analogy between impacting droplets and coalescence-induced jumping of droplets. Because in these 2 processes, what happens is that you have a excess surface energy because of this maximum spreading diameter, once again, which has to be converted into kinetic energy as the droplets take off from the surface. And without going into too much detail about this, let's say the calculations, if you draw this analogy, you can actually fairly nicely write down the exact contributions of different let's say, energies which are there. And this gives you, towards the end, after, let's say, writing a 30-page, not 30, this one was shorter, 25-page JFM, this gives you a very simplified, let's say, prediction, which is if you sum up the Ohnesorge and bond numbers, and if they are of the order 1, then the drops won't bounce. And this is nice because, well, Ohnesorge 1 and bond 1 were already the intuitive limiting cases that we already knew from before. And what is kind of satisfactory is that, independent of the Weber numbers, most of the data points sit across this line. Of course, there are some deviations which we sort of understand, but then in the leading order, this is a good enough, let's say, prediction for this let's say, transition from bouncing to non-bouncing. And another reason why I bring this up is because this is also one of the papers from which I get most of the comments from, let's say, people who are not from PoF. And people, when they write emails, they're mainly worried about this very simplified equation that seems to work, but probably should not work. But we can think about that at some other point. But with that, so to look forward, so I kept like let's say 5 minutes for what do we carry on. So what do I and all of us carry on from here? Is that okay? In PoF, I got such a good freedom, like such a nice freedom to work on several topics. I showed you, like, basically in the parameter space of all the things that I have done, it's one slice of drop impact problems. And I could at the end, well, have this group, which is called Computational Multiphase Physics Lab, short for it shortens to COMFI. That was a good coincidence. And with this, what we learned, what I learned and what we learned together was that we could do, let's say, high fidelity numerical codes, for which this was an amazing place to do that. We used mainly Basilisk, but also other codes that we have in the team, and we all benefit with this. And of course, we could also extend this to non-Newtonian liquids. There were scalings. I mean, the scalings were more reduced order models, or more, let's say, the theory was more reduced order models and more scalings that I showed you now. And of course, great and active experimental collaborations with many of you, but also outside PoF. Because of being here, it was always super easy to do. And of course, several industrial partners. And what I would also leave behind, what we take away and leave behind from here as well, 4 very nice people, among others. So Ayush, who is now doing his PhD on viscoelastic singularities and breakup and so on. So you saw him talk, you saw him speak last week. Aman, who also gave a seminar. So this was all planned, by the way. So he gave a seminar, I think, a few weeks ago on inertial contact lines. Gyandeep, who defended his master thesis amazingly yesterday on singularities with surfactants. And of course, Somili, who did not give a talk yet, but then I decided to show the work that she has done with soft impacts over here. So that's also what we can carry forward. And of course, one thing that I really learned from my time here is that really the open source codes are the way to go. That might not come out that well from my talk here because I did not talk about numerical codes at all. But that we can rectify by doing just one last thing, which will take 1 minute, is that this part here, so this code that you see over there. So in fact, if you know a bit about non-Newtonian fluids and viscoelasticity, you know that this equation, well, which is linear, so it's sigma p goes as g times a minus I, it's fairly linear. A is the order parameter, or this is the strain, if you may. And the nasty bit of this equation hides inside how A evolves in time. And this is basically a time derivative of A. Okay, so it's also a linear relation between the rate of change of A and A. But since if you have to do, and this is something which again I learned here from Jakob, that if you have to do frame invariant, if you have to make sure that this A evolution is frame invariant, then you must solve this nasty equation that you see over there. And of course, okay, forget about that detail, but essentially you have to solve this equation. So if you know about numerics and if you know about these codes, you know that this is challenging to do in 2D, but it's extra challenging to do it in 3D. And one of the things that we could do because of the time spent here and by talking with all of you here was to extend this in 3D. So I show you one case here. We have filament that first stretches out. So we start from 0 stress configuration there, and we let it stretch out first, and then we let it go. And and you can see that, let's say if a Newtonian or a viscoelastic filament, it's a 3D simulation, but I show you one slice of this 3D simulation. So the axis symmetry of this problem is a result, not an imposed condition. And you see that it doesn't break if it's elastic enough. So this is also something that we developed, and this is one of the codes that for the first time we have developed in the group that I have developed, which is open source from the very first line that we wrote down in the script. So from that point onwards, this entire thing is open source. But with that, I will just leave you with the summary. We spoke quite a lot about this, but also, well, thanks to all of you. Sorry for being slight over time by 5 minutes. I planned 45 minutes. And also, PoF was a nice place, but of course, what we all know is it's not just the place which matters, it's the people. And of course, it's all of you who have contributed in several ways. It's a small subset of everyone that I could think of who have contributed to this journey of 7 years. That was always fun and encouraging to have. Well, with that, I leave you with this peculiar case. With this peculiar case of Weber 9, and hope this peculiar case would remind you of me when I'm gone.